Hi everyone, welcome to AI Crack channel. This is Akash Gingwar and today we'll be studying limits lecture 3 and we'll be talking about standard limits and expansion series in this lecture. So let us begin a lecture with sin x by x and x by sin x when x is approaching 0. Now the interesting thing to note over here is both of them are actually equals to 1. But since we know that both of them are actually reciprocal to each other and it's highly improbable that for x approaching 0 sin x would be exactly equals to x, right? It would be highly improbable or impractical, you can say, that sin x would be equals to x. That's why this ratio is 1 when x is approaching 0. So in that case one has to be bigger than the other one, right? Makes sense. Now to understand that, let's try to plot the graph of x and sin x individually. So we have y equals to x looking like this one, right? So this is our y equals to x. Now if you want to plot sin x, it would look something of this sort. Now interesting thing to note over here is x is always greater than equals to sin x in this case, and this equality is coming when x is 0. But what we are dealing with x is approaching 0, x is not equals to 0, x is approaching 0. So for x not equals to 0, it is safe to say that x is greater than sin x, right? Now when x is greater than sin x, x by sin x would be greater than 1. It is safe to say that, right? Now if we take gif function of x by sin x, that would be 1. But if we take sin x by x, gif of that, it would be 0 because this is lesser than 1. Although it's closer to 1, but still lesser than 1. Limiting value is 1 only, right? In this case, for x by sin x, limiting value, the actual value would be somewhere, 1.000001, something of this sort. And for sin x by x, it would be 0.99999. So limiting value is 1 only for this case and for this case. But when we take gif, this would come out to be 0, and for this one it would come out to be 1, right? Now you can prove this with the help of L'Hopital as well. When we are finding limits, in that case we can differentiate both numerator and denominator. We'll be getting cos x by 1. Now this is exact 1 and this is something lesser than 1. Something lesser than 1, right? So in that case, this entire quantity would be less than 1. And same goes for the x by sin x. When we apply L'Hopital, this is exact 1, this is cos x. And when x is approaching 0, this won't be exact 1. This would be something lesser than 1, right? So in that case, this would come out to be greater than 1. Now, the opposite case is for tan x by x. Again, x is approaching 0 and we have to understand tan x by x and x by tan x. Same logic, both of them are actually 1. Limiting value is 1, but one has to be bigger than the other one because it's highly impractical to say that tan x would be equals to x when x is approaching 0, right? Now we know that x equals to tan x only in case when x is 0, right? When we are talking about x is approaching 0, so when x is exactly equals to 0, x equals to tan x. That is the only case. In other cases, tan x is greater than x. If we plot the graph over here, it would look like something of this sort. This is our tan x. So you can clearly see that tan x is greater than our x, right? In terms of magnitude. Okay. So that's why tan x by x would be greater than 1 and x by tan x would be less than 1. Very close to 1 but greater than 1 and lesser than 1, right? If you take GIF of this one, it would come out to be 0. If you take GIF of this one, it would come out to be 1, right? And now that we have understood these two limits properly, their graphs, their values, their GIFs, everything, you can also try these things for these two limits as well to understand their behavior. But the main thing is common: sin x by x, tan x by x, sin inverse x by x, tan inverse x by x, and their reciprocals. All of them, when x is approaching 0, they all are equals to 1. The limiting value is always 1 when x is approaching 0, right? Now let's look at second standard limit of today's lecture, that is 1 minus cos x divided by x square. Okay. So in this case, we can use two methods to derive this one. So let's look at the method 1. I can write 1 minus cos x as 2 sine square x by 2 divided by x square, right? Now we have limit x approaches 0 I'll be multiplying and dividing by 4 over here, x by 2 whole square. So what I did, I divided by 4 over here and multiplied by 4 over here. Okay, and we have 2 sine square x by 2. Now this entire limit is 1, right? So that's why 2 by 4 multiplied by 1, that is 1 by 2 is the answer. So what we did over here, we just converted this x square into x by 2 whole square, because we had an argument of x by 2 over here, and then use the standard limit over here to find out the value, right? That was the first approach. Now one thing I forgot to talk in the previous standard limit, that was when we are saying sine x by x is 1, limit x approaches 0, that x means anything. It can be, let's say, sine of tan x divided by tan x, limit x approaches 0. So what are the conditions? These two arguments should be same. If we have tan x over here, we should have tan x in the denominator. If we have x square, we should have x square in the denominator, and both should approach 0 as x is approaching 0. In that case, this value would be 1. Okay, and same goes for the other standard limits as well. Now in this case, we use that only. We had x by 2 in the argument, so that's why I had to convert x by 2 over here whole square, and then we use the standard limit, right? Now in case of method 2, very simple, you can use L'Hopital over here. 1 minus cos x, that would be 0 plus sin x divided by 2x. Now again, it's a 0 by 0 format. You can use L'Hopital once again. That would become cos x divided by 2, limit x approaching 0. In this case, answer would be 1 by 2, right? Now let's look at this example. We have limit x approaches 0, tan x minus sin x divided by x cube. Now, whenever there is a case when I'm not able to proceed with the trigonometric expression, I tend to convert that expression to sine and cos, right? So let's do that over here. I don't see anything else over here, so let's convert that into sin x by cos x format. Okay, so we'll be using sin x by cos x minus sin x divided by x cube. Limit x approaches 0. Now let's take sin x as common and see if anything useful forms. Cos x minus 1 divided by x cube. Now what I can do, I can split this x cube into two parts. The first one would be x and other would be x square. Why? Because I can see 1 minus cos x forming over here. I can see sin x by x over here. So I am seeing two standard limits forming over here. Limit x approaching 0. Now this one becomes sin x by x. Now this one becomes 1 minus cos x divided by cos x, and we have 1 by x square, right? So eventually it becomes 1 upon cos x, one limit, sin x by x, second limit, and third limit would be 1 minus cos x by x square, right? Limit x approaches 0. Okay, now this one is 1 only, because 1 by cos 0 is 1. This one is 1, we have proved that, and this one is 1 by 2. Now we have used the algebra of limits very conveniently over here. This one was existing, this one was existing, this one was existing, so that's why the product would exist as 1 dot 1 dot 1 by 2. So the answer is 1 by 2. Now let's solve this question. So we have limit x approaching pi by 2, 1 plus cos 2x divided by pi minus 2x whole square. Now I've made a thumb rule for myself. Whenever I see 1 plus cos 2 theta, I tend to write 2 cos square theta, right? So let's do that over here. X approaching pi by 2. So this becomes 2 cos square x divided by pi minus 2x whole square. Now this is not a standard format. We have cos square in the numerator, but we have some kind of argument in the denominator. So we should have sine square and similar kind of argument in the numerator to make some sense, right? So for that, let's do some adjustments. So we'll be writing this as 2 sine square pi by 2 minus x. And to create this argument in the denominator, I'll take 4 as common, because we have square over here. So I'll have to take 4 as common. So this would become 4 pi by 2 minus x whole square. Now this entire equation becomes 1, right? This entire limit becomes 1, because we have sine something approaching 0 divided by that 0 only, right? Because x is approaching pi by 2. So, and this limit is 1 by 2. So the answer would be 1 by 2. Now let's solve this question. So we have limit x approaching 2, x square minus x minus 2 divided by x square minus 2x minus sine of x minus 2. So we have limit x approaching 2, and we have x minus 2 as a factor over here, as a factor over here, and also as a factor over here, right? So it has to do something with x minus 2, right? So let's take that factor out. So we'll be having x minus 2 in the numerator multiplied by x plus 1. So this can be written in this format. And we have x times x minus 2 minus sine of x minus 2. So we can clearly see that x minus 2 is that factor which is creating this 0 by 0 format, right? Let's try to take that as common, basically dividing the entire numerator and denominator with x minus 2. So that would give us x plus 1 divided by x minus sine of x minus 2 divided by x minus 2, right? Now you can see that this limit is not 0 by 0. Why? Because this is a standard limit. This becomes 1, this becomes 3, and this becomes 2. So this is not a 0 by 0 format. So we can now apply the values over here. So this would become 3 by divided by 2 minus 1. So 3 is the correct answer. Now let's solve this question. So we have limit x approaching 1 a raised per x minus 1 divided by sine of pi x. We have limit x approaching 1 a raised per x minus 1 divided by sine of pi x. Now I can see this as a part of a standard limit and this also as a part of standard limit. But in this case, to create a standard limit, I'll have to divide by x minus 1. But for this case, I'll have to divide by pi x. So we have a factor of x minus 1, but over here we have a factor of x. So something is mismatching. Let's try to sort that out. So we have a raised per x minus 1 divide by, we can write sine theta as sine pi minus theta, right? Same, sine theta equals to sine of pi minus theta, right? We have seen that in the allied angles. So this becomes sine of pi minus pi x. Okay. Now we have a raised per x minus 1 divided by, we can take pi as common, so it becomes 1 minus x. Okay. Now we need x minus 1, but we have got 1 minus x over here. So let's take additional minus sign over here and let's write this as x minus 1, right? Now our equation becomes limit x approaching 1 a raised per x minus 1 divided by minus sine pi times x minus 1. Let's multiply and divide by pi times x minus 1 in both numerator and denominator, right? So pi times x minus 1 multiplied by pi times x minus 1.
So this becomes minus 1 by pi, basically pi from here and minus sign from here, multiplied by a raised per x minus 1 divided by x minus 1. Basically a raised per x minus 1 from here and x minus 1 from here, multiplied by 1 upon sine pi times x minus 1 divided by pi times x minus 1. Basically this from here and this from here. Okay. Now we know that this is a standard limit, this is a standard limit, and this is a constant. Okay. So this becomes minus 1 by pi multiplied by, this is basically ln a, multiplied by, this is basically 1. Okay. So the answer would be minus ln a upon pi. Okay.
Now let's talk about Taylor series expansion. And as far as PGDB is concerned, you don't need to understand the derivation part of these series. You just need to remember these series by heart, right? A raised per x, e raised per x, ln of 1 plus x over 1 minus x. You can change the signs over here, sin x, cos x, and tan x. That should be enough. Now you'll be encountering these in case of progressions as well. So basically these series are not just important to limits, but they're also important for the rest of the mathematics syllabus of PGDBA. So just try to remember these by heart, right? And now let's take one example on how to proceed with Taylor expansion series, right? So we have limit x approaching 0 e raised per x minus e raised per minus x minus 2x divided by x cube. So we'll use expansion over here. For e raised per x, we have 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. For e raised per minus x, we have 1 minus x because we have minus x over here. So we'll change the sign. 1 minus x plus x square by 2 factorial minus x cube by 3 factorial and so on. And minus 2x whole divided by x cube. Now we have limit x approaching 0. Now you can see that this 1 and this 1 is getting cancelled out. Now this x along with this x, because minus minus plus is getting cancelled out with this one, right? So this is also cancelled out. Now this x square by 2 factorial and this x square by 2 factorial is getting cancelled out because we have minus sign over here. And we can see that odd powers are being remaining over here. Okay. So we have x cube by 3 factorial from here, and also one more x cube by 3 factorial and higher powers over here. Divide by x cube. Now when we divide by x cube, we'll be getting 1 by 3 factorial plus 1 by 3 factorial plus higher powers of x. And we know that x is approaching 0, so that would become 0 eventually.
So this becomes 2 by 3 factorial, and that is 1 by 3 because 3 factorial is 6. Okay, so 1 by 3 is the correct answer.
So this is how you have to use Taylor series expansion for solving these kind of problems. You might be using L'Hopital or you might be using some other methods in solving these kind of problems, but there might be cases where other methods won't work and you have to rely on Taylor series expansion, right? So that's why you have to understand all sorts of ways. You have to use standard limits, you have to understand expansion series, also you have to understand rationalization, factorization, and L'Hopital, right? So you have to understand these methods to be able to solve all sorts of questions and all sorts of situations in case of limits, right? So today's lecture was till here only, and in the next lecture we'll be solving more problems on these expansion series. And also we'll be talking about the last set of indeterminate forms, that is 1 raised by infinity, 0 raised by 0, and infinity raised by 0. So we'll be talking about the remaining ones, and that would mark the end of limits chapter for PGDBA, right? So let's meet in the next lecture. Thanks for watching.